happy to introduce the speaker of this session, Dr. Jayanti Prasad sir. Dr. Jayanti Prasad has received his PhD from Harish Chandra Research Institute. Then he worked as a research scientist in Inter-University Center for Astronomy and Astrophysics, Pune, and continued there his career as a consultant. Before his research career, he had been working as a physics teacher for 11th and 12th standard students. In 2018, he joined as a data scientist in Embol Technologies GmbH, Pune, and currently working as a data scientist in Digital Intelligence System, DICES, Chennai. He has established high-performance computing grid compute in India with the help of Indian and international funding agencies. His research interests are artificial intelligence, data science, and astrophysics. He has published 180 plus research articles in highly reputed journals and received nearly 69,000 citations in Google Scholar. So without any further delay, I hand over the session to the speaker.
Hello everyone and welcome to this session. As she introduced, I am Jayanti Prasad and I was in academics for a long time after PhD, 10 years, and then I moved to industry. Now I work as a data scientist. So in this presentation, basically I will try to convey some ideas from artificial intelligence and machine learning, which will be of interest to physicists and other science subjects. So basically, here is the agenda of this talk. It's in four sections or 4 parts. In the first part, I will give you a basic introduction of artificial intelligence and machine learning and how it fits in the paradigm of scientific discovery and science. And then I will talk about learning and intelligence, in particularly how we can connect this learning mechanism with physics. And after that I will discuss about natural language processing, which is one of the hottest areas in artificial intelligence, and there are many applications of that. And finally I will show some ideas from physics, how artificial intelligence can help to find new physics and to make new discoveries, or even new physics laws. And I will end my presentation with talking about some very hot topics in artificial intelligence at present, which are like explainable AI, safe AI, and fair and ethical AI. And then I will conclude. So let me start by discussing science. Basically, what are the main pillars of science and how science originated. So you all remember that the most important component of any science is observations or experimental, or the evidence, empirical evidence, what empirical evidence you have. And in other way, it's actually data. So evidence is data. So science starts from evidence and data. Okay, so that is the thing we should keep in mind. It's not about theory, it's the data. And obviously then we need theory to explain that data. Okay, this has been around for thousands of years, basically, at least for 500 years when astronomy started. Kepler, Tycho Brahe, Galileo, Newton, many of these people started with actually data. There was some data on the basis of which Kepler was able to reach what he got, Kepler's laws of motion. Okay, so that started from the data. And then theory, Newton, we all know that Newton developed calculus and many other mathematical ideas. So theory and data, is it working? Yes. So theory and data. Apart from that, there is a third component, a third pillar of science, which was added in early 20th century. And that third component is computation. Okay, so there are many problems which we can't solve with like pen and paper or analytical calculation. Okay, even I will give you one simple example from physics. It's a 3-body problem, or I mean there are n-body problem, but even start with the 3-body problem. It's not possible and easy to solve it in a closed form by just pen and paper. Okay, but using computers, we can even solve n-body problems. You all know that we can simulate systems, and there are many problems which are not possible to solve otherwise if we don't have computers. So that is the under computation. So there are at least two components of computation I can discuss. One is the numerical solutions. Okay, you have partial differential equation or some equations. You can solve them with computers. Okay, and then second part is actually simulation and modeling also. So there are some experiments which are not easy to do in lab or even possible to do in lab. For example, if you are in astronomy and you try to do experiment related to galaxy formation or star formation. So my PhD work was on galaxy clustering and formation. So what you do, you can't set a galaxy to form in lab, okay, or a star. In that way, what you do, whatever physical model and theories you have, you code them, okay, in mathematical equation or simulation models, and then you run the whole thing in computers called simulations. So these third type of thing, sometimes these are called numerical experiment, and they played great role in the advancement of science in last century, at least from 1950s to later on, when the computer became very easy and cheap after Second World War. Okay, and then these simulations you find in all areas, particularly in material science. I think there are many examples, and physics. So that was the third component, is simulation and modeling or numerical experiment, you can call them. Now the fourth paradigm and the fourth component has been added in this list, which is data-driven discovery. Okay, it's like you have huge volume of data. Now you just crunch this data and do something with it and get some information out of it, develop new insight. That's a data-driven discovery. And I quote here from that paper I have given reference there, you can check that. No longer restricted to data analysis, machine learning is now increasingly being used in theory, experiment and simulation. A sign that data intensive science is starting to encompass all traditional aspects of research. So that data is playing a very significant role in all areas of activities and even including the scientific research. So I will come on this issue of data and science, basically how it is important in physics, but I just change the gear and come on this very big idea, very high level idea that we have seen 4 industrial revolutions, and revolution means something which affects everyone in one way or other way. So first industrial revolution was around 18th century, and it came from this steam engine and all kind of machines. Okay, then these machines, they enhanced human capabilities in doing things and made life easy. After that, there was electricity in the second industrial revolution, and we know that the world changed completely after coming electricity. And then 20th century, we saw electronics and computers in 1960s, 70s when they became common. Okay, and so many things happened with computing. Now we are in 21st century and we are going through another revolution, which is called fourth industrial revolution, and that has many components. And one of those components is artificial intelligence, machine learning. Okay, so now one question is that why AI today? Today means in last 20 years. What happened in last 20 years so that we see the discussion of AI everywhere, and there are so many applications of AI in all walks of life, whether it's a business, it's entertainment. Two things we can point out. Two of the driving forces behind this AI revolution. One is this Moore's law. So Moore's law, what is that? That computing power is doubling every 18 months. Okay, so it's a very broad sentence I said, but there are many things in that. But roughly the computing power is increasing. If you, I mean, here the levels are too small, but actually this range is huge. Okay, it's huge. From even if you take from just 2000 to 2010, you can easily find this graph on Google search. You just do the Moore's law, you will find it. And then then there are levels also how the electronics and computers were made. And the last component, which is not very visible here, is we are very close. We are going very close to that, which is the quantum computing regime. And before quantum computing regime, there was this integrated circuit IC regime, basically. Correct. And before that, we had semiconductor valves and all kind of power thing. But we are almost here. We have not entered into the domain of quantum computing because we don't see many quantum computers around. But the power, computing power will increase exponentially, basically. That is the thing. Storage, computing, and the communication, all three capabilities are increasing. It's not just the raw computing power, it's the storage power and the communication also. So this is the one reason that the computing power. And second thing is the data explosion. So again here also you can see that how the data is increasing, and it's an exabyte, it's a very large unit of data. So basically there was some sentence somewhere that the 90% of the data what we have at present was created in last two years only. Okay, so that growth is also the exponential growth. Now we have lot of computing and we have lot of data, so we can crunch that data and we can get out or get some insight out of it. But just these two things will not work. We need smart algorithms also and the numerical techniques also. And there was some progress in that direction also, algorithms timeline. So some of the algorithms were there for quite long time, like for example this logistic regression, linear regression. Linear regression was known even in 1600 something also, that astronomers were using it. But the new thing came like after 64, this recurrent neural network, Bayesian network, and particularly the algorithm like back propagation, which I will explain, reinforcement learning. So many of these things were some sort of developed in last 50 years. So before 2000 or even 99, we had algorithm, but there was neither data there nor computing there. So these algorithms were sitting idle, and many people thought that these algorithms will not make any difference, even they will not work. Even 1980s there was this sense that this neural network, they will fail, they will not work. Okay, and then for 20 years there was no funding to the research in that area, and it is called the AI winter. But again, 1990s, lot of things happened. And then last 5 years there have been very interesting development. I will come on these 3-4 algorithms which are making lot of noise in everywhere. Basically they have created so many applications and so many things, like the sequence to sequence model, attention and transformer. So many of you may be familiar with like ChatGPT and similar tools. So anyone can ask question at any point. In case you have any question, just raise your hand and ask question. Otherwise there will be enough time at the end also. Okay. So I am giving one example, one breakthrough in artificial intelligence, that is of ImageNet. So what is ImageNet? It's a huge database of millions of images, and they are in 20,000 categories. Okay, and one challenge was put that can we write down a machine learning algorithm which will be able to label these images. I mean supervised learning. Once you train the model, then you give an unknown image and the model should be able to label it. So up to 2012, the accuracy of machine learning model was not very good. It was poorer than the human labeler. Okay, but after 2014 there has been tremendous progress in that direction, and the competition is still on. You can check this website. People propose different algorithms and they check the accuracy, that which of the algorithms are doing better. But in 2015 actually the algorithm, they crossed the human limit in accuracy. Means the machine learning model were able to label these unlabeled images better than a human being. Okay, so here is the graph for that. We are touching almost 100% accuracy. And the similar technology is used in many other fields also, like image recognition, face recognition, and many other areas. So the take-home message from here is that this technology has become quite mature now. Image recognition technology is very mature now, and there are many applications of it. Okay.
Like.
So whenever there is any breakthrough in AI, it is called image-led movement. Okay, that image-led movement has come. Now, apart from these images, there is another major area of artificial intelligence, and that is called natural language processing. And there is a lot of work going in that direction. And what is happening is that research done in this area of language is actually helping in other areas also. I will explain that even in science also. So in 1997 there was one paper called long short-term memory, and this paper has these many citations. So this was one major breakthrough. Basically, it's a neural network of a special kind which has memory units. I will explain it later on. But it was not that much used there, although it was developed in 1997. But in 2014, this group, they created a model called sequence-to-sequence learning with neural network, and where they use this architecture, long short-term memory. And this sequence-to-sequence model can be used in many tasks like language translation, question answering, text summarization, and many other issues, labeling images. Okay. But the big bang happened in 2017 when this paper came. Attention is all you need. And this paper has 76,000 citations. Each proposed a very different kind of architecture or neural network. Okay, which was what they called is attention. It does not use recurrent neural network. I will explain. It used something called attention. Okay, so that attention was like very big thing, which is later on, developed for models like ChatGPT and GPT. And then another model came, this BERT, and then finally 2019 we have something called GPT, generative pre-training models. Okay, so you can see that some of these people who are just researcher in 2014, just a postdoc and researcher, now they are CEO for very big companies, including OpenAI, the company which created the ChatGPT. This person, he was just researcher in 2014, and now he is chief scientist of the company which created the biggest some sort of invention in AI technology. So that this timeline is too short. Now progress is happening too fast, and it's surprising that some of the people and researchers, they have been working in AI area for 50-60 years, but they have not got that much fame, recognition and breakthrough as these guys are doing. Some of them are even under 40s, these researchers. So now question is, what exactly is AI? I am just changing the gear for common, how we define AI, because everyone is talking about AI. AI is everywhere. So this is a book. It's quite popular in AI community, Artificial Intelligence in Modern Networks. There is a 4th edition of this book. Russell and Norway, they are the author here. So they have a lot of discussion about AI, but they wrote these books long time back, 25 years back. Even that time they did not have any idea that this thing will become so big in next 10 or 20 years. So they give one table that if we can build a system which can think humanly, 4 categories they have outlined here. So we can call the system AI system if it follows one of these things, if it falls in one of these categories. So this part was taken, and this is the same which was proposed by Alan Turing in 1950s. It's called Turing test and Turing machine. Okay, it's acting humanly. So what this test is, this one. There is a examiner sitting here, and there is a human and there is a computer. Okay, they are behind the wall. The examiner can't see them. So examiner will type questions, and either machine or the human being will reply the answer. If the examiner cannot differentiate between the answer given by machine or the human being, then we will call that machine has got artificial intelligence. So that was the Turing test. So what were the requirement of Turing test? If we want to make a Turing machine, then obviously natural language processing, the machine should be able to consume the natural language, process it, and then create it or synthesize it. So these three things are very important for any artificial intelligence system. That firstly to understand the human language, second to process it, and then to create it. And then knowledge representation is also there, that whatever the artificial intelligence system learns, how it represents that knowledge. And then reasoning is there. And the fourth point is that machine learning, it should have the machine learning ability. So what is machine learning ability? It's learning from experience or data. I will give you a definition later. And then people added these two more components, is fifth and sixth in Turing test. One is called computer vision and second is the robotics. So the intelligent machine should be able to understand its surrounding or environment, okay, by looking around. So that falls under the category of computer vision. And third thing is the robotics. The intelligent machine should be able to manipulate its environment. This is what robots do. Now a generalized Turing test can be listed in terms of these capabilities, the machine having these capabilities. Okay. So this list is also interesting because this gives us some sort of various streams of artificial intelligence or the various branches of artificial intelligence. Now at present, some people work in this area of natural language processing and knowledge representation, but the most active component is machine learning. So machine learning is that writing software and program which will learn from the data without being hard coded. Okay. So what is machine learning? Machine learning is said to learn from experience E with respect to some class of task P and performance measure P if its performance at task in P as measured by P improves with experience E. Yeah, so this is one of the definition of machine learning. So it has term for experience. So what do we mean by experience? Experience is data. Task, there are all kind of tasks. Classification can be one task, gradation can be another task, and there can be other task. And performance, the mismatch between the prediction and the ground truth is called some sort of we can call it loss. Okay, or accuracy, we can also identify accuracy for that. So this is machine learning. Now, machine learning has many components or many types of. So the most common is supervised machine learning. So what happens that in physics generally we know the laws of physics. So we give the input and the laws of physics, and the computer program will give us output. For example, if you are doing a simulation, a projectile motion. Okay, you know the equations, you give the initial position or the boundary condition and you get the final outcome. So that is a normal way of doing thing what we do in physics. But in supervised machine learning, what we do is that actually we give input and output, and then we get some model out of it. Okay, so basically the computer program, it learns mapping between input and output. So there is supervised learning, there is unsupervised learning when there are no labels, where the computer program, they discover pattern themselves in the data. And the reinforcement learning is there, where we give the constant, we keep giving feedback to the computer program so that it improves its performance. And here is another picture that artificial intelligence is a very broad area that I discussed. Within that there is a machine learning, and then there is one particular branch called deep learning. So far anyone has any question or anything? Please feel free to ask any question. This is important. Okay. Now there is another thing called data science. It is also very much in discussion. Okay, I work as a data scientist. So what kind of science is data science? Because scientists have been dealing with data for very long time and always. So data science is not something which is very new or which came just in last 20 years. It has been around there. Okay, but yes, there is some structure like in the data science. What are the things we should be knowing and what are the things we understand? What we cover basically. So data science combines maths with statistics, specialized programming, advanced analytics, artificial intelligence and machine learning. So these are the fields which you should be knowing if you are interested in data science. And most of these things are common to physicists also. Okay, like mathematics and all these things. Maybe this component may be different, but these are the things which are considered in data science. But data science is a very systematic way of finding solutions of problems which are of practical importance or business importance. Okay, so that the target is very fixed, that there are business problems and you have to find solutions of these business problems using data. And that's what the data scientist will do. Okay. So what are the steps they follow, for example? The first thing is the business understanding, use case discovery. So whenever we get some problem from somewhere, so the first thing we do is that what we can do. You have some data, someone has given us some data, huge volume of data. What are the use cases we can make out of it? Okay. Or use cases means how we can add values to the process, value addition by using data available. And so once this thing is clear that we have found this is the use case, then data collection part is there. Okay, we request for the data, what kind of data we need, structured, unstructured, then the data is collected. And then data pre-processing, cleaning, featureization and all these things happen. Then the data modeling part comes. That now we have the data and we have to find that what kind of mathematical models or machine learning model we should be using for this data. Whether neural network would be good or linear regression is enough, or we should use decision trees, or what we should be using. So that is the data modeling part, and it needs lot of experience also, because to find out what will match to what. There is no one size fits solution to all problems. And once the model has been created, then it needs to be evaluated. So what is its performance, accuracy, okay? And then once we are satisfied with this thing, then the model is deployed. It is made available for other expert to use, or the company or other people to use in some way. Like for example, if we create an image recognition solution, okay, so we will host it on some website somewhere where people can upload their image and then it will recognize that image. So that was the second part, and now I'm changing here, and it is very close to physicists basically. I especially put this thing here just to connect the two different areas, physics part and the machine learning part, because people who are from machine learning, purely not from physics, they may not appreciate the power of these equations what I have written here. Okay, but we physicists, we know that we have very, very powerful equations and they have huge many. Look at the conditional probability. I think most of you are familiar with this expression, correct? What is conditional probability? So it is like probability of getting y given that we already have x. It depends on the joint probability between x and y divided by this py. It is some kind of normalization. Okay. So is there anyone who has not seen this equation before? I don't think anyone is there. And the Bayes theorem is there. It comes from this equation, and it's a very beautiful equation basically. When we say that learning from experience, this is exactly what it captures. I will explain how it does it. So this part is called prior. Okay, we have a model, and this is a prior. This is called likelihood, and this is called posterior. So we update our knowledge about certain models by using data. For example, we know something about someone. It's called prior knowledge of that. Okay. For example, it can be mass of some particle or some energy scale or something we already know from the past experience. Now we get the new data. Okay. And using that data, we create a function called likelihood. And when we apply that likelihood on that prior information, we update information about that parameter, and which is called posterior. So you can see that posterior is a model, and here it's model. So we are incrementally improving our understanding about the physical world we are living in. So this equation can be interpreted in that way also. I will give more example of it. So this is one of the most important equation I consider. And then you can see that you can read more about it when you do the data analysis course and various places, that how it works. That it's called marginalization, and A is model, as I said, and B is the data. Okay. So let us give you an example. You are doing a line fitting, y is equal to wx plus b. So in data science, we don't write mx plus c, we write w. W is weight and b is bias. And this is our data. So then we create a likelihood, it's a Gaussian likelihood. And what does it mean is that whenever we will have a data is equal to y is equal to wx plus b, there will be a noise component to it. Okay, and in most cases that noise is modeled as Gaussian noise. Okay, and in that situation the likelihood function becomes like this one, and this part is nothing but it's chi-square. So it's chi-square minimization is written in a very glorified way here. Basically it's the same thing. This can be a question also in exam. Prove that the chi-square minimization is nothing but maximum likelihood estimation. So either you maximize this thing or you minimize this thing, and you try to find these parameters. So here it is like, before fitting the line, we may have some idea about these parameters W and B as a prior parameters. So this is exactly what the machine learning does. We have a model, and the model has some parameters. And in the beginning, the values of these parameters are random. We set them some random number. But as we do the training, the values of these parameters are improved. Okay. So that's exactly what the machine learning training is. That this loop can be run again and again, because what is here posterior can become prior for next iteration, and so on and so forth. So you can keep running this loop. Okay. So now it's very important again here, this probability distribution. So there are two main type of artificial intelligence at present. One is called discriminative and another is called generative. So that discriminative models or the AI, basically it is all about the conditional probability. So what is the probability of this picture being of a car, given that this is the data we have? Okay. So this is the type of question we are trying to answer in classification. That this is the data, and what is the probability of its label being this or that? Okay, whatever labels we have. Okay, so let me come back to the point. I was talking about probability distributions, and this is very important to understand two kinds of probability distribution. One is this conditional probability distribution. Conditional probability distribution is that probability of data being of type Y, given that we have data is X. Okay. And second thing is the generative model captures the joint probability Pxy. So, or just Px. So what we are doing, I will just generalize it, that how human being actually learn. When we go around and see things, okay, we see patterns, all kind of patterns, either in text, shapes, objects, and from these patterns we built some mental models of probability distributions. joint probability distribution, that we know that if it's a car, then it will have 4 tires also. Okay, so these conditions we already know. Or we have this joint probability distribution that, for example, shapes of fruits. Okay, from our experience, we know that most of the fruits are rounded. So if we make a probability distribution of that, then the rounded shape will be peak at rounded, but there will be shapes of other kind also. So we mentally make these probability distributions. And same thing can be done in machine learning also, this PX, joint probability distribution. So these models are called generative models. So if you go on a website, it's called this person does not exist. Okay. So if you just keep refreshing the page, you will see that this website creates images of people who don't exist. We just give some condition, like you give the gender, age, something, and very nice looking and very realistic picture of people who never existed. This is the generative AI. And how it is happening? Once you know the probability distribution of something, let us come to in physics. Physics, there are all kind of probability distribution, correct? And whatever data you have, that is actually realization of some underlying probability distribution. And if you can figure that out, okay, like in quantum mechanics, you have wave function. In some kind of that is also the similar thing, that if you have wave function, you can get out of whatever you want, correct? If you have the full wave function. So here also, if you have the full probability distribution, it's very easy to get one of its realizations. It's a simple, like, I will explain how this thing will work, that this person does not exist. You collect millions of images and create a probability distribution on a grid, like 400 by 200 plot in pixels. So you will see that, and you plot the probability distributions, okay, like color or gray area, whatever. So there will be some particular probability distribution, and then you run your random number generator something and ask him that, can you create one more realization of this probability distribution, then it will spit on the picture, and so forth. So I think it should be easy to understand that once we understand this joint probability distribution, it's fairly easy to get one of its realizations. And even if we know this conditional probability, we can get any one realization of it. We can put condition like chat GPT. So now what is happening is that chat GPT has shown, it has read all the data and it has seen all the patterns, okay, in the text data, internet, wherever. So it has a mental probability distribution in. Now if you ask a question, it will condition that probability distribution with your question, and it will expect answer to that. You understand that how you can condition it, like you have X, okay, this will be a good answer here because it's a unlabeled thing X, then you can get out of it one of its realization, and you can condition it. So that's how it works. And we have to learn the mapping between the data and labels, the features and labels. And once we learn that, then we say that our model is trained. And then we use that trained model to predict the label for unknown data. So two important things are here, the features and the labels. Okay. So here it is like our data is always type xi, yi, where xi is a data instance and yi is the label. And the mapping can produce this output as a continuous variable, then we call it regression, or it can be a discrete variable, then we call it classification. So this is our model. And the main idea is to minimize the mismatch between the predicted output and the actual output. Now our model, this f can give us output for a given x, okay? And this is what I call yi hat, and we already have the true output, and then we can minimize it. So minimizing this process is called optimization. So we have to find the parameters which will minimize the loss or the mismatch. It's called optimization. It's a big area, but before going to that, let me come to this loss function. So there are many kind of loss function. One loss function is this mean squared error. Okay, you have seen it like in the chi-square minimization.
I have not normalized it, but this is how it is. And another thing is the cross entropy. It's called cross entropy. You may be knowing something called Shannon information or entropy. It's a summation of minus pi log pi. Okay, that's the expression for that. So it comes from that. And then we have activation function also. Like this is a linear model, but if we want to make a non-linear model, then we have to map this linear output to non-linear. We can use some activation functions. These are non-linear functions. And one of them is sigmoid, but there are many other like this one. So this sigmoid, it actually squeezes any data. If we have the data between minus infinity to plus infinity, so it can squeeze that between 0 to 1. Okay, it's a non-linear function. And the similar non-linear function are here. So why I am showing this non-linear function is that basically our purpose is to understand or to learn a mapping between input and output. And in most cases, that mapping is going to be non-linear mapping. Okay. And in order to get that non-linear mapping, we have to use this non-linear function at multiple places. So let us come to the most common and most famous algorithm, which is based on artificial neuron or perceptron. So this is what we believe that human neurons are. They have the multiple inputs at left, called dendrites, and they are all squeezed, and the one output is created and it goes to axon. Okay, after applying some non-linearity. So we model that in this way, that this is a neuron and these are dendrites. They are taking multiple inputs, and these multiple inputs are summed after applying some weights to them, and then some bias is added to it, like zero value, and then here the activation non-linearity is applied, and then output is produced. So these two things are equivalent. Okay. So this is how the biological neuron work, and this is how the neuron in machine learning works. Now the magic happens when we stack these large number of neurons together. Like in the human brain, we have billions of neurons, and every neuron has thousands of connections. Okay, and all our cognitive capabilities, they are the result of these connections. Same thing can be done in neural network also. But before that, I will just highlight one thing called optimization. That's very important in machine learning. That how to find the best fit values of parameters to a data. Okay, so there are many algorithms there. Some of them are based on natures, and I have some work in optimization also. I work on a algorithm called particle swarm optimization, which is used in many areas. But in machine learning, what the most common algorithm is this gradient descent algorithm. So how it works in this way. So you want to find the value of the parameter theta at which this function j will have a maximum value. Okay. So you do this iteratively. You start with some value of this theta parameter, and then you find out the direction along which there is the fastest change in the loss function. And then you keep doing this thing and you will find the best fit parameter. But for example, in case of linear fitting, this is how the loss function is. And you can see that the loss function can be differentiated with respect to this weight, and we get this thing. This is this delta j by delta theta. So we can update these parameters. Okay, and the same thing for the classification part also, we write this entropy thing. But in neural network, now we come to everything is put together. Now there are multiple neurons, okay, and we can have either multiple outputs or one output. And this is the input part. So some of the features of this neural network are, it consumes input data of a fixed size. Like if your input data is a vector, it has dimension 10, then all the data points should have the 10 dimensions. So like here in this case, 3, 4, 5, 6, 7, 8, 9. So it will consume a data vector which has 9 components. Okay, and it will give output these 4 values. Now you have to propagate the mismatch, the gradient of mismatch backward. Okay, that is the most complicated thing, and the major breakthrough happened due to the algorithm called back propagation algorithm. I will explain that, and on the basis of this architecture, we can build very big network, means very large number of these layers of neurons, and then it is called deep learning. So deep means many layers. So what actually happens that this deep learning model or neural network, it learns the features present in the data at different level. Okay, it abstracts the features. So deep learning allows computational models that are composed of multiple processing layers to learn representation of data with multiple level of abstraction. Okay, so this is very important. I mean, you can go back and check this paper. This is a very famous paper, Nature Review. These methods have dramatically improved the state of the art in speech recognition, visual object recognition, object detection, and many other domains such as drug discovery and genomics. Deep learning discoveries intricate structure in large data sets by using the back propagation algorithm. Okay, and there are many applications of deep learning, but the backbone of this deep learning is back propagation algorithm, which is actually the nothing new. I mean, physicists know this chain rule of differentiation. Okay, I will not go in detail of what does that mean. That if this is y and there is some weight here, so we cannot directly differentiate this output with respect to weight sitting at this end, but there are in between output, so we can apply chain rule. So this was a very famous paper written in 1986 it's published in Nature, and it revolutionized the field of deep learning. Basically, this is the first time when a concrete implementation of the algorithm was given and some results were proposed. But again, not much happened after 1986 to maybe up to 2000, because there was not much data available. These deep learning models, they have very large number of parameters, so they are data hungry. And then people have made all kind of deep learning neural networks. Some of them are too complicated, out of basic building blocks like this one. Okay, so if you want to know just two key properties of artificial neural network or deep learning, just two, so what are these? The first thing is there's the universal approximator. So there is a paper there, it says that any kind of non-linear relationship between input and output, it can be modeled in terms of a neural network with at least one hidden layer. Okay, no matter what your actual function is. So this is a very big discovery and insight. Approximator means they can solve any problem. So this is a very big some sort of selling point of these models. And the second important property of these is the automatic feature learning. So what happened that in other machine learning model, you have to learn the feature yourself, like what are the attributes on the basis of some decision will be taken. Okay, handcrafted features like some human being is sitting here. But in deep learning model, actually they themselves learn the features. I will give you an example that 30 years back when deep learning was not there and people were trying to find people were trying to write code which will identify human faces or match faces, for example. Okay, so then someone was trying to create the features of human face, that there should be a nose, eyes, the distance, geometrical proportion, this, that, so many ifs there in that thing, and then applying those logic and trying to identify a face. But that's very tricky, it doesn't work, basically it failed. But in this case you don't have to do that. Neural network will automatically learn the features, and some of these features may not be explainable, that's another issue, but they will learn layer by layer. So I will give you an example of text modeling. So data, if you look at the data, we generally have two kinds of data. We have the numerical data and we have a symbolic data. So numerical data, you can apply all the mathematical operation, plus, minus, division, and everything is possible. Even the distances between two data points, you can find it out, how close they are. But the symbolic, that is not the case. Like if you say that the mango plus apple, what it is, there is no answer to it. But actually this deep learning and machine learning model, they give some mechanism to do such type of operations also, which we can apply in text. So data you can numerical, symbolic can be continuous or discrete can be ordinal, nominal. Ordinal means we can have first degree, second, third, where there is a ordering, or it can be just a labeling like roll number. So when it is just like a roll number, which is a nominal, just like in data, it doesn't make sense to add the roll number of two people or subtract the roll number of two people, because that has no meaning. Correct? So text is exactly like that type of data where okay, we can replace all the words used in a text by some labels and some number. We call them IDs. But we can't do any mathematical operation on them. So there is a mechanism. The challenge in modeling text, I already mentioned that we can't do numerical thing with text data. But there is a way that we can come up with these equations, that king minus man plus man is queen. So this is a very famous result there somewhere, that when this input was given, the model gave the output this one. Okay. On what basis? Let us come to this. How it is done? You have a text like this one. So first time you create a vocabulary. Okay. Like in common English language, there are 40,000 or 50,000 words. So you map every word to some integer, 1 to some maybe 40,000. And second thing, then you create a vector of that size, vocabulary size. And if you want to represent some word, so now there is a place for every word in that long vector. Okay, make that value non-zero, otherwise put all the values zero. I mean, you can imagine what I am talking about. So these are very long vectors where most values are 0 but one value is 1, corresponding to the word where what it is representing. It's called one hot encoding. So this is the first step, was that you assign ID to every word. Okay, now words are gone, you have integers. But again, that is not enough, you can't do operation on it. But then you do one hot encoding. Here some operation is possible, like at least AND or type of operations are possible. Correct? So there are vectors and they have only one place where it's non-zero. But again, that is not very useful, it's a very long vector and sparse. But there is a technique, now it's a pure linear algebra, you can think about it, how it can be done. That if you have a very, this one hot encoding vector x, which is a, let us consider it's a column vector with 10,000 columns, and only at one place it is 1 and rest it is 0. Okay, so you can always find a matrix which will make it a lower dimensional vector, but it will be a dense vector. Its value will be like floating point number. So there is a scheme, it's called embedding, where actually every word can be represented by a lower dimensional vector in a space called latent space. And most commonly it's a 300 dimensional space. So once you have converted all the words into vectors, then it is possible to apply mathematical operation. And that is the place where, so there is a library called World to Back and Globe. So it's all probability and statistical mechanics, statistical learning, where people have found out the vectors corresponding to most commonly used words. Now you can go on internet, download the library, get the vector for any word and apply the operations. Or similarities. Okay, you want to find a similarity, for example, from Chennai and cricket, for example, two words, or some other word. So you can do that. And even in chemistry and material science also, there are research paper and things like that. It has this material here, okay? So it was also one hot encoded, and finally it was converted into latent space. And then you can see that all kind of similarities can be found between Even you can find similarities between research papers, research topics, materials, all kind of things. If you can do this, if you can get those things into latent space. So this is a very important insight. So here also, like in chemistry, I was looking at some material science paper that this is a chemical formula. Okay, but first it is converted in something called Ismaili. This is a kind of a string, and once they are converted into string, then we apply the same techniques which we use in text processing, and can do classification, regression, or similarity identification. So this was the technical part. Now I will come on some lighter part of it. Okay. So 3 revolutionary neural network architecture, as I mentioned, one was the sequence to sequence model. It was based on this LSTM. So what it does is that basically it takes input like a sentence, okay, and it generates output which is again a sentence. So if we train this type of encoder decoder model for machine translation, it works very well for the question answering. If you have a list of, for example, 10,000 sentences in English and Tamil, okay, you can feed that data to this neural network architecture, and next time if you give a English sentence, it will give answer to you in Tamil. Or if it's a question answering system, it can learn that. It is based on this recurrent neural network where actually the output is feedback to the input. So that was one important architecture. Second was the attention. So attention means when actually, okay, you have read some paragraph and now some question is being asked to you. So whatever is present in that paragraph, not everything is relevant to your question. Okay. So you can train neural network in such a way that they give attention to only those portions of the input or text which are relevant for your answer. So these are the attention models. And there is a paper, again it's a very famous paper. And then finally came the transformer, which was a type of architecture that we don't need recurrent neural network. We can use just this attention model, and we can create very big models like this GPT on which this ChatGPT is based. So these are the 3 important neural network architecture, and on the basis of this GPT is there, you can go and check basically the recent report from 27 March 2023 that what advancement has been made on this ChatGPT and GPT. So physics and AI, I will just highlight 2 papers. You better to note down the reference and read the paper yourself basically. That will be more useful. It's a physical regulated paper. So what it says that okay, it's an important paper. So they have used this neural network to discover physics concepts like Copernican heliocentric model. And under physics paper is this one, AI Feynman. So what this guy did, this research group, they actually discovered 100 physics formula which are given in Feynman's lecture in physics using this machine learning model. It's a big project, but it's a very interesting and inspiring project. So this was for physics. Now there are some issues, and I don't have much time, and these are very big issues like explainable AI, safe AI, fair AI. So explainable AI is that in most cases these machine learning models, they work as a black box. They will give you just output for a given input, but they will not give any explanation that if this candidate was not selected, then what is the reason why it was not selected. Okay. If this person was not approved the loan, what was the reason? So there is hardly any explanation. Particularly these neural network based models are opaque. Okay. So there is a lot of discussion going in that there are certain domains where we can't use AI model just as a black box, where explanation is needed, like in finance. Okay. You are an advisor to some investment firm and you say that okay, you buy this stock because my model says this is the best, but then you have to give some explanation or some medical treatment, or if it's a defense a decision. Okay, you say that I ran the model with all the input and it says that you should fire now. But then that will not work. And Safe AI, even Tamil Nadu government has a very comprehensive document, you can check it, it's on internet, that the outline has been given there that if you are some sort of rolling out any AI solution, then what are the things you should keep in mind for safety purpose. And fair and unbiased AI, so it should not be like racist and all kind of things are there. So I think I will end here and I will take questions. And please feel free to get back. I keep writing about machine learning on my blog on Medium, so you can check some of my articles there and post there if you have questions. Yes, so and here these are some of the references I used. Particularly for physicists, there is a review article called a High Bias Low Variance Introduction to Machine Learning for Physicists. Another interesting paper is this annual review paper, that statistical mechanics of deep learning. Very interesting. Discovering physical concept with neural network. Physics informed machine learning. There is a paper. And at the last, I have given the link of my this Medium page. And there are two special reports. One was published in Nature in 2015. It's called Machine Intelligence. It's around 40-page report. And one report was published in the similar time in the Science magazine. It's called Rise of the Machines. So both of them are very interesting article collection. So I think I'll stop here and take questions. Thank you very much.
Okay, question? Yes, go ahead.
Yes. Correct. New? Yes, you can generate new things. With the generative model, they are generating new arts, new poetry, new music, new everything. I mean, you see every time. This is how these things are. So basically, generative model, they have creativity also, and that is the threat. That is threatening, because many people are some sort of under this impression that good number of people will go out of business. Maybe a machine learning model can write a very nice poem, can draw a painting and everything, things which are generally associated with human creativity, then what human beings are for. So that's the challenge. So lot of discussion is going on there. If you check the internet, hundreds of experts, they have requested certain organizations to stop working on advancement of some of these models before understanding what will be the implication of these things. Yeah, any question from this side, or please feel free. Your question can be very simple also. It need not to be very complex.
Actually, last month I heard one Nobel laureate give a lecture. He was very afraid that the AI-driven material discovery will suppress human creativity and intelligence, because when we do traditional DFT-based calculation, we know the mechanism behind that and intuitive knowledge about that new material, why it is created, why that particular functionality is there, all these things are coming up. This lead to next level of discovery or something. But here we have a lot of data we give, then based on that it predicts some material in between what is happening and which these things are the big bottleneck to move towards AI-driven approach for materials discovery, like that he mentioned. What is your opinion on that thing?
I think this is a very transient time, okay, particularly next 2-3 years, because everyone is confused, even experts are confused, even the best experts. That, like exam paper, students are using ChatGPT to submit their answers. Okay,
Yeah.
and researchers are full length papers are being written by ChatGPT. Is that correct or not? Okay, so this is a tool. No one knows that exactly how good or bad it is. As you are saying that these things are actually giving new materials, new discoveries. Okay. And some of the problem like the protein folding problem, many problems. So this is exactly the time when actually the AI machines are just getting smarter than human beings. So it was a race, okay, and then where we were ahead, and machine was taking us. Now it comes to 2022, where the machine has actually just overtaken us. So when people use ChatGPT, you can check my blog that I ask 100 questions to ChatGPT from all areas, from philosophy, physics, maths, whatnot. And I was some sort of very impressed with the answers. Okay, all the answers are well thought of, well. So I think almost everyone is very sort of impressed or shocked with the situation, basically. That way, from government agencies like it's Indian government or European government, various councils are being made, and how to regularize this thing, and how to safe, how we can make safe AI. And so I think it is very confusing time. Even the science journal editors, they are discussing how to deal with the situation. Okay. Even one of the paper, actually one author was like ChatGPT or someone was put as an author. Then should we actually give credit to the thing also? Like you write a paper, give to student. The student will proofread draft and all of things. But what happens that when the student take that draft, give that to ChatGPT, and it does everything nicely, better than the student, then should that student get credit for it or not?
Yeah.
Then who should get the credit?
Not ChatGPT.
So that is the question. So I think it's very, very confusing. So better to keep following the trend, what experts are saying. Recently, one of the fathers of this Hinton, Professor Hinton, he was the person who wrote that back propagation paper. He was boss of Google AI. And then he resigned few months back. He said that when I will be in the company, I will not be able to criticize and give my input openly. So better to resign. So he resigned from that position.
Okay.
So many people are like trying to understand how to deal with the tool. Basically, it's like something has come in the market and people were not ready.
When we do machine learning driven material prediction,
Yes.
when we have group of data already exists in the database and give, then within that it can able to give better model.
Yes.
But predicting outside of some new material discovery or some little different domain, then the predicting ability is a big disaster, I can say. The how to get a model more generalized for particular class of properties or particular class material or some kinds of thing, whether it will evolve that direction, and then maybe we can this model will be generalized for designing new solar cell material, for example, or hydrogen storage material, or thermoelectrics, like that something will evolve or
It will
predicting.
evolve. I think like someone asked me that, okay, how it is different from Google? Google give you information, you said. It's different because it is synthesizing the answer.
Yeah.
Just like human being, you ask 10 people, just remembering and spitting the output, correct? They are synthesizing in our mental picture, right?
Yeah.
So these generative AI, they are doing exactly the same way. Like what answer ChatGPT gives to you, it's very unique to you. So it's not that someone will ask the same question, will get the same answer. No, it will be different answer. Even at a different time, answer will be different. So what it is doing is that it has all the vocabulary and all the words there, and it chooses which of the words to use and to create an answer. Not like Google, which will just pick a document and piece of a document and give information. So that synthesizing part is some sort of a threat to human creativity. I mean, that's the biggest thing. Because human being, they had some sort of this superiority complex. Okay, that only they can synthesize things, only they can write poems, they can draw painting, create a new music. Okay, like machine can't create a new music, but that's not the case actually. The generative model, because generative model has seen all kind of poetry, for example. Okay, it is trained on everything. Now we understand what kind of poetry clicks to people and is possible, and it will create that. or personal advice, you ask ChatGPT about your personal situation, whatever, it gives you answer. Like if I say that, okay, I want to give to this university, this is the background, I want to give a talk on AI, can you please suggest that what are the 10 topics I should be covering? So it will give me a better list than what I can actually think of, given the situation.
Okay.
So that is the,
Okay. Good.
okay then,
Thanks, Deb.
if there are no more questions, yeah.
Where to draw the line to have a safe age? How to draw the line?
Yeah, so drawing line is, it will be a fuzzy line actually, it will not be a clear-cut boundary, correct? Because what happens that finally it matters, human being they have a finite experience, like one person maybe have read 500 paper or maybe 1000 research paper, correct? But the machine learning model has read the 50,000 or 1 million research paper. So that machine has a far more experience. So we can't deny this thing that, okay, no, machine will not do it. Finally it makes the performance. So I think there is a lot of work need to be done in the policy field and regulators, either at the research level that, how to safeguard various things basically. A publication, I said the publication thing, because publication will become obsolete basically. Correct? When the machine themselves, they can directly read the data, write the paper, send the paper to some referee. Referee is also on the bot or on the intelligence system, checks it, just reply this thing, okay, it get accepted. Or maybe then there is another bot who is reading that paper, and the whole process keeps going on.
Whether this data-driven approach is applied in financial market, that is a
Yes,
huge potential.
very
Money.
much it is done.
Okay. Whether any firm is already doing, suppose an investor using this approach for future investment.
Like,
Is there anything?
I mean, many of my friends who are PhD in physicists, they are working with big financial institutions and banks.
Okay.
Okay, some of them are trying these things.
Mhm.
So yes, they are doing. But the thing is that physics, there are things, underlying rules in physics, correct?
Yeah.
So in financial market, these things are evolving.
Mhm.
So there is no underlying, like in physics, we can write down all the physical concept maybe in one page, blueprint of the whole universe, correct? Conservation and this and that. But that is not the case for many of the fields, where the data will play important role. Physics, it is not clear that whether this data-driven thing will be like it will overtake human creativity. That is not clear. Like unified theories, for example.
Okay.
So it's not clear that whether a machine learning or AI model will come up with a better grand unified theory than what is in the market. So that's not clear. But you can ask some very complex physics question to ChatGPT. Most probably it may not work on that.
Okay. Yeah.
Yeah. Okay then.
Okay. Thank you very much.